450 papers published, over 500,000 downloads, and probably over 5 million miles traveled in a year. Please welcome DK back.
Okay, thank you. So good morning, everybody. So today's I'll be talking more on the kind of the topic many of the people have been thinking about. How do you design convergent HPC, deep learning, and big data analytics software stacks? Okay, so that is the kind of the focus. Yesterday, I presented more on the distributed training, what are the kind of challenges, but I'll go up a little bit today and then see how to design these stacks. So these are the data. I'm sure all of you are familiar, like currently the number one system, the Summit, is delivering 143 petaflops. And of course, the field is moving towards exaflops. And just 2 weeks back, we got this announcement, at least the first announcement for Argonne National Lab, coming up with this A21 system with Intel and Cray. So that will be trying to develop exaflop in another like a 2 years time frame. So in this context, as many of us have been working on, there are of course HPC, big data, and deep learning. I showed this figure yesterday also in my talk, and there is a very nice dependency going on between these 3 subfields. And in that context, people want to actually run some workflows which have all these components, like you want to run HPC stack, traditional HPC, as well as like big data and deep learning. So then the question is, how do we try to run all these things on the single platform? Either it is a physical platform or it could be also in the cloud. So a lot of people have been talking about this kind of convergent software stack. So in fact, in my group, we have been working already for the last several years. So I'll try to show the vision of our work and how we are trying to achieve. So what do we mean by convergent software stack? So let's say you have a typical HPC cluster or an environment. You have physical compute nodes. You can have some resource manager like a Torque or Slurm. You can have some parallel file system, Lustre, GPFS. So the question is, most of the time people run these kind of MPI jobs. So the challenge is exactly on the same hardware and the software infrastructure, can we actually also run Hadoop job or Spark job or deep learning job without the requirement of multiple clusters? So many times currently in the organization, you can have like an HPC cluster sitting here. There is a Hadoop cluster sitting there. There is a deep learning cluster sitting somewhere else. And then people are moving data back and forth between these clusters. And as you know, moving the data is not the best way to achieve good performance and scalability. So we want to make sure that exactly on the same system, we want to run all these different jobs. So many of you might be knowing, like let's say if you are a sysadmin, on a given HPC system also nowadays, there are many different MPI libraries. People take different MPI libraries, make modules available to them, to the user, so the users can actually choose any particular MPI library linked to their application. So the question is, can we try to do exactly similar kind of things for the other ones? So that's what I'll be talking about. So in order to design this kind of a software infrastructure, we always start with the programming models, because that is the kind of the middle abstraction, as many of you know. So this is where, like, if you think of the traditional scientific applications or like MPI, PGAS, CUDA, OpenMP, OpenSCC, you can have also like the Hadoop Spark. So all these kind of things are the programming models. And then at the bottom, I call this like a supply side, at least from my research perspective. We have all the different networking technologies, multi-core, many-core architectures, and the accelerators. And these technologies give us a lot of new mechanisms and features. So the question is, how do we take advantage of those and try to deliver the performance and scalability at the application layer? Okay? And of course, we have to go through some kind of a middleware, but this is where the communication library and runtime comes in, so that we take advantage of all these features, pass it through the programming models middleware to the applications. So either we can do it in a layered manner, or also we can do some co-designing, working across the various layers, so that we get even better benefits. So in this context, I'll try to introduce at least 3 major projects in my group, what we have been working, and how we are trying to provide synergistic relationship between these projects so that you can actually deploy these stacks on your system. So that's what I'll be talking. The MPI projects, this is the high performance deep learning. I talked a little bit about that yesterday. And then the HiBD, which is the high performance big data analytics library. And once I introduce this, I'll also try to introduce this, some new development has happened. I talked about that yesterday also, like a commercial support we are trying to provide through this Exascale Solutions organization. So let's first start the scientific side, which is the MPI and PGAS. As many of you know, like this, the distributed memory model, MPI, that is the message passing interface, that is the common programming model for all the scientific applications these days. Of course, you get shared memory that is within the node. When a number of cores are there within the node, you can get cache coherency, but you cannot scale that cache coherency across the nodes. And this is where, looking forward, a lot of work is taking place with respect to PGAS, or partition global address space. So these are the kind of models where you provide logical shared memory, not cache coherent shared memory. And different models like global arrays, UPC, OpenSMEM, those kind of things are coming up. So in this context, I introduced this MHAPPY's project yesterday. So we almost worked on the day one of InfiniBand when it came in the October 2000. The initial standard was there. In my group, we were working on Myrinet, Quadrix, those older interconnects. So we were the very first ones to jump in. And then we had the very first version of MPI over InfiniBand running in 2002, almost 17 years back now. And then over the years, we have worked on a lot of enhancement. This project is continuing for 18 years and going strong, and is currently being used by more than 3,000 organizations in 88 countries. These are based on voluntary registrations. And a few months back, we crossed 500,000 downloads just from our site. Of course, our stack is also integrated into a lot of other stacks like Red Hat, SUSE, OpenHPC, vendor software stacks. We don't keep track of those. But in addition to that, we have been enabling a lot of top 500 systems over the last decade through this software stack. And I also indicated yesterday, like we're a partner in this upcoming TAC Frontera system. So this is just trying to show a very quick snapshot of how the number of downloads are increasing over the years. We are in a very steady rise for the last several years. So this is the big software architecture we have been working on, trying to focus. We started with scientific computing. Again, it is also having impact on the deep learning. I talked about that yesterday. I'll go into a little bit more details. But at the top, we support all these MPI, PGAS, hybrid MPI, PGAS also. We take care of all the different networking technologies. We also take care of all the different platforms. And this is where is our, the innovativeness come. First, always we try to do research because we are in an academia. We publish the papers. And in 6 to 9 months, we typically take these designs and then put it into our software stack. Okay? And even though being from a university, currently we have almost 150 servers continuously doing QA testing. Okay, 24/7, 365, these machines are running continuously. When we do the designs, we push the things into our code base. And now we have capabilities within 36 to 48 hours, we know whether the design is working or not. And then we go through a lot of different kinds of regression, unit testing, performance regression, all those kind of things. And also we have access to a lot of large clusters. So before we make a release, we make sure that everything works. And then we push the release, and then you can just download and run it on your large system, and it will run out of the box. That's how we are able to maintain this ecosystem. So there are a lot of different versions out there. I'll talk about these 3 versions. There is a cloud version, energy-aware version. There is a monitoring tool, InfiniBand network analysis and monitoring, and some micro benchmarks. I may not have time to go over all these things, but I'll primarily focus on the first 3. So this is where, the HPC, we try to enable the best performance and scalability with these 3 stacks, both host-based and GPU-based. So let me go into a little bit more detail saying how we come up with some innovative designs. And this is where we try to deliver the best performance and scalability. I'll try to touch a few of those things. Then also I'll talk a little bit about these are the traditional x86. I'll give some numbers on the open power, ARM. These are the next generation systems that are coming up. I'll also talk about a little bit of application scalability, best practices, and then how to exploit the accelerators, especially NVIDIA GPUs. So these are some of the numbers. Over the years, we try to show how different adapters are trying to provide the benefits. So here it is all these numbers are taken in my lab using very unified stack kind of things. So the left-hand side is trying to show small message latency, like half of round trip is a ping pong. So currently, we see across the adapter, I don't have the SDR numbers yet. So these are the EDR and Omnipath. So you get around like a 0.98 microsecond kind of things, MPI, across the node. And for large messages, of course, the bandwidth matters. So this is where you see like the Omnipath or the EDR are performing very similar. And then this is the bandwidth, the left-hand side, unidirectional bandwidth, the rate at which you can pump the data. So currently, if you see here, it's like around 12.5 gigabytes per second. If you do a multiplication by 8, it's like 100 gigabits per second. And bidirectional, we have 200 gigabits per second. But these are only the point-to-point. Most of the time, you see this point-to-point performance people try to show. But when you try to design a stack, just the point-to-point is not sufficient. We try to take a very holistic view, trying to address all the different components inside the MPI and to make sure that application level you get the best performance. Okay? So just to give you an idea, so recently we introduced a thing called a cooperative rendezvous protocols. So this paper was actually presented at SC18. It was a best student paper award finalist. So think of like an MPI stack. How many of you know by eager protocol versus rendezvous protocol? I think many of you know. So the rendezvous protocol is basically used by large messages. So if I want to send you a large message, I first send you a request, and then you give me an ACK, and then after that, either I can put the data or you can do a get from me. That has been the traditional kind of designs for over last 20, 30 years. So we thought of saying that, is that the best way? Can both sender and receiver participate in the data transfer? Okay? So we took a very common example. Like, for example, think of like your friend is there 3 miles away, 3 hours drive away from you, and you need to deliver something to your friend. Either you drive or he or she drives. But then another option is that both of you drive and come into the middle point. Okay? So that will have a very good savings in time for both of you. So that is the kind of protocol we have taken. So if I want to send you a message, once both of us are ready, or depending on which one comes first, we can actually cooperatively participate, okay, and take care of the data transfer. So that's why we say like it's a cooperative rendezvous protocol. Okay? Nobody has done this kind of protocols into the MPI stack. So if you do like this, these are some of the numbers. We are trying to show like a 1500 cores, like Graph 500, COMD, Mini Ghost. You see at an application level, you can actually get 19%, 16%, 10% kind of performance. Okay? Because we are trying to keep all the cores busy all the time and trying to minimize the communication overhead. And in fact, this is coming out in our release. Actually, today it will be released. It's a later part in the day. Today you will see the public release will be coming out, and you will see this protocol is already incorporated. So that is the kind of like a point-to-point. Now, of course, there are a lot of focus on collectives these days. And I think there is one hardware called SARP. I think there is a talk today, I think after the lunch. Mellanox has brought out this kind of support in the network. It's very similar to what Quadrix used to have many, many years back. So that kind of SARP, we have actually integrated into our MPI stack. So here you can see like with the average D dot all reduced time in the HPCG, if you have this kind of enable the SARP-based collective, you will see like you will get around 12% performance benefit at an application level. So then this is another design we actually put in the all reduce. All reduce is becoming very important. Yesterday I talked about that from the deep learning side. And of course, similar kind of things also exist from the traditional scientific computing side. So you introduced a new concept called data partitioning based multi-leader design. So it was actually a supercomputing 17 paper. So those of you who are familiar with like a little bit of MPI runtime, people have used over the years like a hierarchical collectives, okay? So that means within the node, if I have so many cores, one leader, you define one leader, it actually reduces the data and exchanges information across the leaders from other nodes and then broadcast the data within the group. That has been the traditional. But if you follow that kind of a thing, you will see only one leader is doing most of the work. All the other cores are just sitting idle during this all reduce. So we tried to come up with a parallelization scheme so that it is a data partitioning based multi-leader design. So if I want to do an all reduce of 256 megabytes of data, and instead of one leader, I can define a 16 leader, because nowadays there are so many cores. within the node. So each one is trying to do a part of the reduction so that everybody is remaining busy, and at the same time, they're exchanging communication in the network so that overall we should be able to improve, and that's what it shows. So for example, for large message sizes, if you see like a 32K message size, we are able to improve the already time by a factor of 2.4. So once again, like I'm trying to give a lot of examples from inside the library, how we can optimize all this communication. This is a CMA-based collective. This is CMA means cross-memory attach. It is based on like a Linux module, so that you can actually, instead of within the node, when you try to do the shared memory, like I typically write to memory and then somebody else reads, it is a 2 copy. You can reduce that to a 1 copy using the CMA. And here you can see this was a paper from IEEE Cluster 17. It was a best paper finalist. You can see this then, it is in a log scale. So for very large messages, compared to other MPI libraries, we can do like a factor of 2.5, 3.2, 4x better kind of things for the collectives. And very recently, we have moved to this new one I introduced briefly yesterday. It is like a XPMEM. That is a kind of a newer module which is coming out, kernel module. So we have taken advantage of that. And again, here we are trying to provide a true 0 copy kind of communication, and then we can again reduce this the collective time by a factor of 1.84. And then similar kind of designs, it is not just for the basic point-to-point and collectives. Now we can also use for data types, because a lot of scientific applications use data types, and this is where a lot of time you lose, and we are trying to accelerate those type of data type operations. So in fact, this paper will be presented the next month at IPDPS. It has been selected as a best paper nominee. So here you can see across the different MPI libraries, the data type operations. This is like a 3D stencils, this is a milk data type, this is a NAS MG. We are able to improve by a factor of like 5, 19, 3 kind of things. Okay? So that's why we are taking a very holistic view and trying to see all the different components of the MPI library and how we can accelerate those. So then another challenge many times in the MPI stack is that asynchronous progress. How do you handle, like for example, if I'm trying to send you a very large message, as I said earlier, like it's a rendezvous protocol, but if you are not ready, if you are busy in the computation, even you cannot handle my initial request. Okay? So this is where like people have been working on a lot of asynchronous progress design, but people typically use some additional cores or some additional threads. So here we came up with a new design. You don't need any additional things. Without any dedicated resources, we'll be able to do asynchronous progress. This was actually a Euro MPI 2018 paper. So now if you do this, take a look at some of these numbers. So this is like the time for P3D FFT compared to even other stacks like our own design versus the new asynchronous design compared to here Intel MPI 2019. We can give you actually 26%, 33% performance benefit. And this is even HPL. Many of you know the HPL people try to run the best performance. Even for HPL, we can even try to reduce or here performance in gigaflops, so the higher it is better. We can give you like a 12%, 29% benefits using this kind of new design. So these are all already gone into our public versions. So then, of course, now, I mean, those are the x86. We have been focusing a lot on the open power also, as the Summit and Sierra, those machines are coming. So here we are comparing with Spectrum MPI, which is the default MPI in these systems. Here you can see like intra-socket. We can deliver like in a 220 nanoseconds, we can actually do MPI operations from core to core within this open power platform. Then these are the large message latency, unidirectional bandwidth, bidirectional bandwidth. They're very similar to Spectrum MPI. So then these are some of the ARM numbers. ARM again has different versions. We support all those different versions, but here I got a clearance just to present these numbers only. This is the ARM Cortex A72. So here again, we can try to do within the node, we can do the transfer in 270 nanoseconds. Like within the node, we can actually communicate within the socket. So then, if you put all these things together, like these are all the different components. If you put it together, here are some charts. Like these are the spec MPI benchmarks. And that is a kind of a standard benchmarks people use. So here you can see, like if we put all these things together, here we are comparing with the Intel MPI 18. So as you can see at an application level, we can give you also a lot of benefits for different kinds of the benchmarks. We still lose out in the Leslie 3D, and we are trying to optimize that part. And these are some numbers from the TAC Stampede 2, trying to show scalability. So here, like a 4K, 8K kind of course, we get very good performance and scalability for a lot of range applications. These are the CICS, and these are the older KNL kind of things. We are able to get good performance. And as we are actually trying to demonstrate all these kind of things, so we actually created a new compilation of best practices. Because many times, within the MPI, there are so many parameters, almost 100 parameters, 150 parameters you can modify. If you tell me like, okay, give me the best performance on this application, on this platform, I can spend like almost 3-4 weeks to give you the best number. So what we are trying to do is as a community effort, so if you go here like this page under best practices, we have a lot of like initial list of applications, and we give credits to all those people who have contributed, so that if you are trying to run similar kind of applications on your platform, you can take a look at this page and then see which parameters you need to adjust, so that you don't spend again another 3 or 4 weeks. So those are the kind of the pure host-based things. On the GPU, I talked about this yesterday. We do the CUDA-aware MPI design, which we started in 2011, and over the years we have been continuing on that. So this is the latest kind of things. We call it the MAPIS to GPU direct RDMA. So here we have around like 1.85 microsecond. We can send data from a node to node over the InfiniBand. And if you see this CUDA-aware MPI, the kind of benefits, so here I'm trying to show a HUMD Blue, which is a molecular dynamics application. So here you can see like compared to without the basic CUDA awareness, if I provide the CUDA awareness, this is our GPU direct RDMA, you can see like higher is the better. We can actually deliver almost 2x performance improvement for these kind of applications. And then I showed this yesterday. In fact, we are in Switzerland, in Lugano. We have been working with CICS folks for last several years, and as well as Meteo Swiss. This is a kind of a flagship project. We are trying to really drive the weather forecasting here. So as all of you might be seeing your iPhone and see the weather and all, so we are actually collaborating with CICS for the last several years. And we are trying to continuously give performance, and Sadaf is sitting here. I mean, every time little bit performance gets disturbed, we get an email, okay, saying what happened, okay, because they're so performance critical. So we have been continuously working on that, and I'll show you actually we have some new designs. These are the numbers on the kind of Summit system. So these have the open power with NVLink 2 and Voltas. So we have optimized our GPU direct RDMA stack here. So if you take a look at this is like a multiple GPUs on the same node, okay, with NVLink 2. So when you do the MPI communication, so here we are able to achieve like 70 gigabytes per second for large messages. Almost like peak. We are able to exploit the peak in the NVLink 2. Using our MPI level communication, so they are connected. And these systems don't have the GDR copy, so that's why you don't get very good performance. We have been trying to work with some of the sysadmin there, so if they can put the GDR copy, we'll be able to even reduce that latency. Otherwise, we get like around a 5.36 microsecond latency. So this is the new thing which we have been doing. This Cosmo application has a lot of data type processing. And we have been continuously now, what we have done is, we have done like a kernel-based and GDR copy-based one-shot packing. So most of the time, this packing kind of things gets done in the host. So we are trying to identify kernels so that we can do it in the GPU itself. And here, if you see with this kind of new designs, this is like a DDT bench from Milk, and then this is the communication kernel from the Cosmo models. Compared to what we have so far, these numbers have been taken on the CICS CRACS term. So you can see we can improve that Cosmo model by almost factor of 10. Okay, so this will be rolled out in the next our release, and then you people can actually take advantage of that for your Meteo Swiss applications. So that shows like the purely on the MPI side. So let me go into a little bit of the deep learning. I talked a lot about that, so I'll try to compress this part. So here again, 3 things one can take. I talked about the Horoward MPI stack yesterday, so that is the kind of the stack which is emerging for deep learning. So within that, you can have any of the MPI stacks. You can also have a Nickel, which is the library from NVIDIA. And we have done a very thorough in-depth study, so this will be presented at the CC Grid 19. But the one I want to highlight, the green bar, the higher is better. This is images per second. And the yellow bar is actually the ideal, what you can achieve. And then using our MPI version, this is the green, you can see we are coming very close to the ideal kind of things. So we are able to give the best performance as the hardware can provide. And I showed this number. This is the all-reduce performance because a lot of these deep learning applications are heavily dependent on the all-reduce. So we have been trying to optimize that in our MPI stack. And here we are comparing with the Nickel 2 from NVIDIA. So you can see here, like for small messages across the large messages, we can give you like a 2.5x better or 1.7x better kind of things at the all-reduce. And that leads to, this is like the ResNet 50 training. This is on a DGX2 node with 8 voltage GPU. So as you can see, when compared to Nickel, this is the Nickel 2.3. We have not done the 2.4 evaluation yet. You can see like you can get around 7.5% higher. But the more important thing is the efficiency. So the red line is our design. So you can see you get very good scaling efficiency as you go into more number of nodes, because through our design, we are trying to keep NVLinks busy and also the CPUs busy, and trying to exploit the overlap. That's what is leading to very good efficiency. So this is the GPU version. If some of you are not familiar, you can just download from our MVAPage page. We try to put all these things for the regular systems. And nowadays, a lot of these deep learning are going through the container. So we are also trying to provide the container-based support. So you can actually take our stack and then link it with all your deep learning stuff. So here there is a very small recipe kind of things. We have also contributed this to the HPC container maker. NVIDIA is trying to maintain that. And if you see with the container, you don't see much performance difference. Okay, so whatever you get in the bare metal, you should be able to get similar kind of performance through the container. So you should be able to exploit that in your deep learning. So then I talked also yesterday about this, the other stack which a lot of people are using, the pure TensorFlow with gRPC. So that is kind of the traditional stack people have been using. So that gRPC we have done, this is the gRPC with the Google RPC, typically goes through sockets and you don't get good performance. So we have done an RDMA version of that. Just like MPI stacks, instead of running sockets, we take it to the native InfiniBand. We have done that with the gRPC. So this is the release. And here again, you can see these are like the red line is our design, and the higher is the better. So you can see that compared to all other designs, whatever is available in the literature, people go through all different combinations. We are able to give you the best performance, the images per second. So again, this is publicly available. If you are using that kind of a stack, please feel free to download and use. So in this context, if you remember, I talked about the MPI. So now you can take any of these our software stacks, either the MVAPage 2 GDR or Harvard with MVAPage 2 GDR or RDMA TensorFlow. Just build it on your system, make the modules available, so people should be able to directly utilize this, okay, so that they can actually coexist with your scientific things. But then the final thing is the big data, because people also want in your workflow the kind of Hadoop or Spark kind of things. And these are the kind of the typical data processing happens in a data center. So on the front end here, you have some of these components, Memcached, HBase. Backend here, you have like MapReduce, Spark kind of things. So what we have done is a lot of these stacks, we have made them RDMA enabled, okay? Like basically trying to bring it to the real verbs level so that you get the best performance, just like any other MPI stacks gets, okay? So I'll not have time to go over all these things, but these are available. We have this project, High Performance Big Data, HIBD. So you should be able to download. All these are like the RDMA for Apache Spark, Hadoop 3, Hadoop 2, Kafka, HBase, Memcached. These are the most frequently used components in the big data analytics. So these again are InfiniBand as well as Rocky. We have support for x86, Open Power, also the containerized version, Singularity and Docker. So in any way, you should be able to utilize these. These are currently being used by around 305 organizations. We have around like close to 30,000 downloads from our site for these stacks. So to go into an architecture, so what we have done, this is like a Hadoop stack. So if you think of the MapReduce, SDFS, so all these things, we have actually not only have the RDMA, but it also has support for Lustre, okay? Think of the parallel file system, so it has support for Lustre. We don't have it for GPFS. We are getting a lot of requests. We'll be trying to work on that. And then also the job scheduler, like a Slurm and PBS, we have also made interface, okay? So you don't have to, as an user, you can just like make a module available at sysadmin, and then the user can just come and directly use it. You don't have to go through all the Hadoop installations there. And recently we also proposed this Hadoop 3.x. So that is a new Hadoop architecture which is coming. It has actually eraser coding. That is the kind of the new designs which are coming. And in fact, there also we have just the first paper accepted at HPDC on that eraser coding. And here it shows some performance benefits. I showed a little bit of these numbers yesterday. So here what shows that like this is the regular Apache Hadoop stack going over IP over IV, but whereas this is our RDMA stack. So this is the latency, this is the throughput. Of course, the lower is better and here higher is better kind of things. So again, so what you can do is like, if you are a sysadmin, you can just download our stack, configure it based on your configuration, what kind of SSDs you have, parallel file system you have, or disk you have, and make this module available. So in fact, we have been working with San Diego Supercomputing Center. Those from US, if you have an Exceed account on the San Diego Supercomputing Center called Comet, you should be able to exactly use this. So they have actually made these modules available, so you just log on and launch your Hadoop job or Spark jobs. You don't have to do anything else. So that's what I mean by convergent stack, so that exactly on the same machine, all these jobs can run in a transparent manner. Similar kind of things we have done also for Spark. We have the RDMA Spark enabled, and same kind of things can happen. You again download these, configure it based on your system specifications, and then make a module available. So these are all the kind of stacks. I just wanted to give an example, saying irrespective of what kind of things you are working on, the HPC side, big data side, or the deep learning side, or any convergent kind of things, we are trying to enable the community. And so far, like, you can download from the issue site. In fact, if some of you have used our stacks, we have like open mailing list and we extend help, but a lot of people are asking for the commercial support. So that's what has started recently, just 2 years back. This is the organization Exascale Solutions. We are actually a sponsor of this event also. You will see that logo here. So through this, actually, we are able to now deliver just like any other software stack, like a ISV, depending on your need, response time, guarantee, all those kind of things. We can satisfy, we can be part of the procurement or bids, all those kind of things. And for last 2 years, we are actually providing services to Lawrence Livermore National Lab. So that is the biggest installation in the US. So all their machines, we are able to provide our software stacks, and then trying to, not just the basic stack, we are able to now work with the application scientist and really work with them to really optimize all the features and trying to deliver the best performance here. So with this, let me conclude here. So as we are heading into the Exascale, actually we need to take a very holistic view of HPC, big data, and deep learning and cloud to design these software stacks. And I presented an overview of how we are trying to do in the community. A lot of people have been talking about it, but we already have these stacks available for the last several years, and people in the communities are already trying to utilize this. Of course, that is just the beginning. As the architectures are continues to be changed, we need to keep on coming up with better and better solutions. So with this, let me just show one more thing. Some of you might be familiar. I just want to show, for the last several years, we are also trying to do an annual MHAPG user group meeting. We call it MUG. And we'll be having the 7th meeting in the August. Some of you here in the audience have participated here in the past. So speakers are being lined up. So Dan Stangioni from TAC will be a keynote speaker. So I think that is the time the Frontera will be coming up. So you will see a lot of new results on Frontera there. We have tutorials from ARM, IBM, and Mellanox lined up, and some of the speakers are being confirmed. If you are have a plan to spend your summer in US, please come and attend our things. So if you're interested in giving some talk, I'll be happy to coordinate with you. So we are trying to create a user base so that everybody learns from each other. So that's how is the idea of here is the users group meeting. So with this, let me thank all the sponsors, but more importantly, as I said, These are all my heroes, all the past students, staff who have contributed to all this work. I just come and visit, but they keep on doing the hard work. So I want to acknowledge them, and these are all our pointers. So with this, I'll be happy to take 1 or 2 short questions. Otherwise, I'm here throughout the day, and then I'll be happy to talk with all of you.